All right, today we're going to talk about a new theorem, but before we do that, I want to refresh your memory on one that we've already talked about, which is the intermediate value theorem. Because both of these theorems are going to have to do with studying what happens between 2 points on an interval of a function. And so they're going to look pretty similar. So to refresh your memory, intermediate value theorem was something we talked about before we talked about any derivatives. We were just looking at limits and continuity. And what intermediate value theorem says is pick a height. So I'll go ahead and pick this height. As long as it's somewhere between my 2 points, between the heights of my 2 points, then what intermediate value theorem says is that as long as my function is continuous, then no matter how I draw this function, at some point I have to cross through that height. I have to cross through that blue line to get from point A to point B. It doesn't matter how I draw it, and it could cross through multiple times. But the key thing is that as long as we're continuous, it goes through those points. Now let's talk about our new theorem, which also has to do with drawing 2 points. So this time I am going to call my points A and B. And what I'm going to do is I'm going to connect a straight line between A and B. And this straight line that I draw is called the secant line. As opposed to the tangent line, which just crosses through 1 point, a secant line crosses through 2 points. So I'm drawing the line that connects these 2 points. Now, I'm about to draw a few different functions, just like I did for intermediate value theorem. And the question we're looking to keep track of this time is there a place where the slope of the tangent line of the function equals the slope of the secant line? So when we draw the curve and we keep track of our tangent line slope, is there a place where that slope matches up with the slope of the secant line, where I can overlap my secant line and know that it equals the tangent line? So let me draw a function. And I'm interested in, is there a place where these slopes line up? So here's a better drawn secant line here. And if I drag it across my function, I'm looking for where the tangent line lines up. Not there, not there, not there. Oh, it looks like about there it does. So that's a place where my slope of the tangent line matches up with the slope of the secant line. Here's another function drawn between A and B. And I'm going to have you pause for a second and see if you can find where this slope of the tangent line will line up. Did you get 2 answers? I hope you did, because it does happen twice this time. It happens once down here and once up here. So the general question is, can I always do this? Is it always true that no matter how I draw my function, I can always have a place where the slope of the tangent line and the slope of the secant line are the same? And the answer will be yes, with some conditions. So I want you to think about what those conditions might be. So see if you can draw an example, a counterexample of a function that does not have the slope of the tangent line equaling the slope of the secant line. And think about why it didn't work. Well, here's a nice easy counterexample, because the slope stays at basically 0. But the problem with this function is that it, unlike our other functions, it breaks continuity. So that's one of our conditions. We need it to be continuous. That happened for intermediate value theorem too. We needed the function to be continuous. Otherwise, our same problem happened. But there's one other requirement too. And that would be if my function looks something like this. Well, that doesn't work because my slope is too tall here, it's too big here, and then we come down, we're decreasing, so now my slope is negative and it can't match this slope here, which is positive. But the problem here is that at this point, I've got a corner. And a corner means that the function is not differentiable. So since we are talking about slopes so much, you might have an idea that this theorem is going to have to do with the derivative of the function. So let me go back to the original example I was looking at, and let's focus in on this place where that slope of the tangent line lines up. And since I have points A and B, I'm going to call that point where the slope of the tangent line lines up, I'm going to call it point C. And so that lets me get some nice, easy XY coordinates, just to make this a bit more technical. So point A is going to be at an X coordinate of A and a Y coordinate of F of A. And then same for points B and C. So using these X and Y coordinates, see if you can think about how we're going to express each of these things. How are we going to express our slope of the tangent line, where our slope of the tangent line happens, and how are we going to write out our slope of the secant line? Because that's what the more technical theorem is going to say. So I'll let you give a few seconds to see if you can think of it. Welcome back, and hopefully you got at least one of these. If we're looking for the slope of our tangent line, let's start with the easy one. The slope of the tangent line, well, the slope of the tangent line at a point is, hey, that's just a derivative. It's the derivative at that point. So it's going to be f prime at the point, which is C. And our slope of the secant line, well, that's just a straight line segment. So if I want the slope of my secant line, then that's just going to be the formula for change in y over change in x. So since I'm looking at A and B, change in y is going to be f of B minus f of A over the change in x. So my x coordinates are B and A, so I'm going to subtract them. This is also going to be an important formula. Not only is this going to be the slope of the secant line, what we're going to talk about later on is this is also going to be the formula for average rate of change. This slope of the secant line. So this is going to be the average rate of change between A and B. So another way to say this theorem is that the slope of the tangent line at some point has to match up with the average rate of change. So if you ever have to find an average rate of something, then this f of B minus f of A over B minus A is going to be your formula. So here's the mean value theorem stated out in a more technical way. And this outlines kind of how we're going to approach a mean value theorem problem. We are going to, first off, check our conditions that we need, which is that we need to be continuous and we need to be differentiable. Once we know that, then we know the mean value theorem has to be true. And so we can guarantee that our slope of the secant line is going to match up with our slope of the tangent line at some point. So this f of B minus f of A over B minus A is something that you're usually going to calculate in the problem. You're going to find f of B, you're going to find f of A, and you're going to do this formula. And you'll get a number, say 5, for your slope of the secant line. And that's going to tell you that at some point, my derivative has to be 5, somewhere in between there. And then sometimes the problem is going to ask you to actually find where that is. Where does the derivative equal 5? So to recap those steps one more time, you're going to check that the function is continuous and differentiable. You're going to find your slope of the secant line, your f of B minus f of A over B minus A. And you're going to say at some point, by the mean value theorem, the derivative has to equal that number. So that's all for now. We're going to try some examples next time, so I'll talk to you then.